we go. Right, hello and welcome everybody to another one of our WBS training free webinars. So just to let you know how this is going to work, obviously this is going to be presented by Alexandre Antonov, and we would ask everyone to please stay muted. You can feel free to ask questions in the chat function and I will relay them to Sasha at the appropriate times. Yeah, if you want to know more about these free webinars, if you go to the WBS training website or the Quant Hub website, then you will be able to find them all there. This will also be recorded and go up on the Quant Hub YouTube channel. But we may as well get on with it. So, Sasha, take it away.
Thank you. Thank you. Good morning or good afternoon, ladies and gentlemen. In this presentation, I will tell about possibilities of asymptotic control and other sort of controls in neural networks. As a subtitle of this presentation is Asymptotic Splines and Constrained Radial Layers. So we'll construct around to these technical achievements. And this presentation is based on our paper with Michael Konikoff and Vladimir Pishobark. It's available on SSRN. Right, so the goal of presentation is following. So machine learning, deep learning, neural networks becoming a standard piece of toolkit in banks and other organizations. As we know, the neural networks has been proposed to first speed up slow functions calculations, for example, based on the heavy Monte Carlo calculations, and to calculate conditional expectations. So you can see a reference here, and suppose this presentation will be done public by WBS. Of course, the application of neural network are numerous, so you can see the references in this presentation also. I will stop on these two goals: speed up of slow function and calculation of conditional expectations. In general, so-called learning points, we try to tabulate our function are concentrated in the main body of the distribution, not in its tails. So typical neural network fitted to observation extrapolate outside of this learning cloud in a totally uncontrolled manner. So it does as it does. Of course, it depends on number of layers. It depends on number of nodes. It depends on the activation functions of everything. Here, our goal is to incorporate extra information, which we have, for example, asymptotics, into neural network construction in order to control these extrapolated values. So many important reasons, such as stress testing, explainability, and so on, are also the reasons to do this work. As you know, for example, recent stress, market stress, which was related to the COVID, then make the very volatile month, such that some of the model were completely out of its good defined area. So that is why it's important to have the asymptotics as close to reality as possible. Let us start with neural network brief description. So actually, this presentation, just I prefer to say, is more to quants rather than to specialists in neural networks. So that is why we'll maybe use sometimes a quant slang and not not data scientist one. But anyway, so this is we share the same math, so we should agree with something. So a neural network is a multidimensional function parameterization. So let us imagine we have our input variables x. So this is a vector variable x of some dimensions. We produce the first so-called layer, applying a matrix W, weight matrix W to this X, and we add so-called bias vector. So on this linear transformation, we apply nonlinear activation functions. Of course, the dimensions of this vector W should be in accordance with the dimension of X. However, the output of this vector B and W not necessarily have the same numbers. It can be different. But nevertheless, we apply element-wise this function sigma to get the first layer value. Then we do the same thing with this first layer. We do this iterative procedure. We apply a matrix. We add a bias vector to get the second element of the layer, and so on. So finally, after some number of iterations, we get a function f of x with a parameterized with theta. Parameters theta will include w's, the weights, and the biases. And this is actually our neural network. Forward-fed our neural network. It's very, very, very easy definition. Just a couple of reminders that each line in this scheme above is called a layer. So as I said, nonlinear functions sigma are called activation functions. Normally they're fixed. They're not, they're not variable. Sometimes they are, but in general not. And the adjustable parameters for neural network are weight matrices and bias vectors. So which are here. Some of them can be fixed, some of them can be relaxed. But again, in general, both of them, W and P, are adjustable. So we move them in order to fit the function. So again, the neural network parameterization of the function is f of theta. The theta is a collection of all the adjustable parameters, W and B. So we can have quite a lot of them, and the general can be several thousand or even sometimes several million. So the function can be very rich, but of course it is too rich, then optimization is not that good, but nevertheless. The parameters of theta are determined by so-called learning process. In quant slang, it's just optimization. So given the points x of p, p rounds for paths, and y of p, this is our answer. For p going from 1 to a little p can be several thousand, several million, several billion, and so on. And a loss function, for example, a loss function can be a simple square, sum of the squares of the neural network and the output value. So we move the parameters theta, our weights w's and b, in order to find the optimal values that minimizes this loss function. This nonlinear optimization is performed numerically. So some numerical solver moves these parameters here and there to get the right way. Actually, that's it. So this is the definition of the neural network. Some features of it. So first, the neural network parameterization is numerically very attractive. Its derivatives, which are of course necessary for optimization, can be rapidly calculated with sort of AD in quant terms or backwards propagation in data science terms. The resulting function f of theta approximates the conditional expectation y of x. Right? So if the points of p are some deterministic function of x of p, then the output, our neural network, approximates the function itself. So if there is no noise, of course, it will have to reproduce something close to the initial function f. A slide about advantages and drawbacks. So advantages are highly efficient, existence of highly efficient and customizable software. So there are a lot of whole set of examples. For example, Keras software in Python. It is free. It has very large parameters control. You can choose whatever W and B you're looking for, different dimension, different number of nodes, and so on. It has bespoke layers. GPU acceleration, cloud, whatever you want. So someone after university can easily implement it and use it directly without any tuning, any thinking actually after all. A good thing is also universality of the approximation and theoretical guarantee of success such that our neural network will be as close as possible to the initial function, given, of course, sufficient data. So if we have billions and billions of points in multi-dimensions, for example, we can always hit the initial function, at least in the biggest majority of the surface. Of course, if you have a 100-dimensional function and 1,000 points, then of course the result is not guaranteed at all. So we need more information. Of course, if we have some extra information, we can help the neural network to get oriented in the correct way. To, for example, to handle situations where we don't have enough number of the points. The drawbacks of neural networks is, of course, in numerical, numerical solving a highly nonlinear multidimensional problem is unstable. We can fall to a local minimum, overfitting other things. Of course, we can struggle against this, having some regularization chunks and so on, but in general, it is numerical solving. As I said, they don't have an asymptotic control. It's population control, neural networks. It's our main focus. There is, by the way, no interpolation control in standard neural networks. So even if the training points are well fit, one can potentially observe big holes, for example, between them. If I have very multi-layer neural network between two little points, we can have large spikes. Sometimes it happens. The theoretical basis of neural networks were several theorems, namely Sebenko and Hornig. They actually came up with a one-layer neural network, saying that it can converge given again large number of the nodes. It can converge to whatever function we use. Also, Kolmogorov-Allnort theorem also states something like that. It's not exactly directly the neural network, but something around that. In our paper, in our SSRN paper, we have a big appendix devoted to Kolmogorov-Allnort. Its proof is not very trivial. However, intuitively, it's not very complicated. So we did this. We have described the proof in kind of quant terms. Maybe without all the conversion things, but we give the intuition of this proof, as well as we have constructed sort of neural network which corresponds to this proof. So in several maybe 10 pages of appendix in our SSRN version can be helpful for people interested in this maths. Right. So the plan of our action is quite easy. So I wouldn't say as everything in neural networks, but So we start with the function f of x. So in the measure we know it's asymptotics, right? So we know them analytically. For example, if we have a Saber model, then for large strides, of course, we can learn some asymptotics, or the function itself can be slow, can be a result of calculation of PD or simulations and so on. So we suppose that the function is slow, but the asymptotics are fast, they're analytical. So first step here, we're looking for a console-varied function such that it has the same asymptotics as the initial function, but can be slightly different in bulk, so in either all directions or partially. So this is our first technical result of this paper. We use a multidimensional spline such that has the same asymptotics of f of x. So we take the spline, and we're sure that this spline will have the same asymptotics as the function. So I will slightly talk about this. However, in the paper, SSRN paper, there is a description of how to stick asymptotics to this multidimensional spline. So when we get this universal multi-control variant function, we subtract from it the function f of x, and to work with the residual function. So this residual function will have zero asymptotics in the directions where we control them. And then we approximate this residual function using a specially constructed neural network with zero asymptotics in given dimensions. So it's pretty simple. So first we take our function f of x, with some asymptotics, then we build multidimensional spline s of x with the same asymptotics. We subtract the function from this spline such that the residual function has zero asymptotics in given, in given directions, and then we approximate this residual function. Easy, but of course technically it's not very trivial. So first, remind of one-dimensional spline. So spline or cubic spline is a piecewise cubic polynomial. So as simple as this, between nodes h of I. So between h of I and h plus 1, we have a cubic spline. So the spline should pass through given values. So for given h of I, we fix the values of the function where we would like this spline to pass through. So as h of I is fixed, so this is the values. And the spline is a very smooth guy, and we will require it, the values, of course, being smooth, well, the same values, otherwise it wouldn't smooth at all. Derivatives are the same, and the second derivatives are also the same. So in the cubic spline, even the second derivative is continuous. Just a little reminder, the second derivative is linear interpolated, and the function itself is very smooth. So these requirements, of course, first that it passes through the required points, then the same derivatives to the left and to the right of each point hi, and the second derivative almost fixes all these coefficients a, b, c, and d, except there are two extra conditions. So in general, these conditions, in general, always these conditions are related to the first node of the spline and the last node of the spline. So we should fix them somehow to finish the job. And the classical spline has zero second derivative at boundaries. So this means that it goes out of the bulk in a linear manner. So let's see how it works. This orange graph is a spline, is a Black-Scholes function. In terms of the log spots, this function like this. Then green points, green stars are the spline nodes, and this blue one is a spline. So we see that it's very good approximation between the points. However, what happens outside, we don't really control. So here we see that this spline goes out using the second derivative equal to 0. So in other words, just linearly extrapolated, like this. So of course, it doesn't know what happens with the function after the last point and the first point, but it goes out as it can go. Now, let's see if we can control the asymptotics of this spline. So instead of 0 in the second derivative, we can choose to fix the first derivatives at boundary points, so arbitrary value. So we can have this hint to fix asymptotics. So suppose that we know again original function in its tails, and we know the analytically the asymptotics. So f minus will be asymptotic starting at point 80, some far point, and f of x equals f plus for x more than n plus 1. So the two extra points line outside of our initial points. So the recipe is simple. We just add 2 points where we start the asymptotics h0, h, n plus 1. And then we will make this spline which passes for this function. So we know the asymptotics and know its derivative, and we're done. So this procedure does not guarantee the second derivative fit, but again, it is possible to have even the smooth fit for the second derivative, such that we can fix the second derivative of the spline being equal to the asymptotic value. So again, there's some tricks here and there, and you can find more detailed description in our paper that helps on the plot. So here we see that green points are initial spline nodes. Red points, red stars, are points where we attach asymptotics. From this point, we know the asymptotic here and here. And as far as the spline is smooth here, we see that it follows almost the exact function. It's not always such a good fit, of course, because if the function were like that between the last point and the asymptotics, of course we wouldn't say that. However, all the good functions, the functions which are has a reasonable behavior can be much better approximated using this information rather than without it. Of course, we have extra information here, and we glue the function spline goes out of its last point. We glue it with the asymptotic here. So in principle, this point, of course, this interval fit the function better. In multi-dimensional setup, we use a tensor product of one-dimensional splines with asymptotic control. Again, you can find details in our paper, and we just can demonstrate asymptotic control effects using example of Black-Scholes price for strike equal to 100 and time equals to 1 in the log scale. So this is two-dimensional Black-Scholes price. This is your log spot, and here's the log wall. So the points, the blue points here, this is the values of the spline, sorry, the nodes of the spline, where it fits in the spline. The red points is where asymptotics start. We suppose that we know asymptotics starting from this region, outside of this region. So we glue these asymptotics to the spline formation to get something like that. So we see that all is smooth with some imperfection, for example. Here. So let's see what happened with errors. Well, according to this graph, all the major problems are aligned outside, of course, of the fitting region. So in this region, all is good. This spikes outside the region, which we call sometimes no man's land. So here we know the asymptotic. Here we know the value of the spline. Here in the no man's land, there is no information. So spline approximates interpolate decision as it can in a smooth way, and often it's very, very efficient. So these errors are relatively very low, because you can see here it goes up to several thousand. And here, for example, with spline without asymptotic control, again, all is good inside this inside the region where it fits the points, but outside we can see here that errors can be really massive. Spline without asymptotic control extrapolates in whatever way, in the linear way. So it is useful, of course, to use this explanation. So now, so imagine we have calculated a certain spline with some values in the bulk. We have calculated the difference between this control varied spline with asymptotic control and our function. And so we would like to approximate the residual function with vanishing or zero asymptotics using the following neural network. So this is sort of handmade neural network. So we propose to use the function which is built with so-called Gaussian bells. So this neural network is a one-layer network. It's a linear combination, lambda I, of Gaussian functions, which we call Gaussian bells, where Ci is the center of this Gaussian bell, and W is its variance. In our experiments, this W is not a matrix, but just a number. Sorry, it is not a matrix D by D, but a diagonal matrix. So just simply a vector. So we would like to approximate our function using these Gaussians, and we know that if we restrict the center and the width, we'll get zero asymptotic. So Gaussian bell, if it's situated inside the bulb, will give any non-trivial asymptotics, but the asymptotic will be zero. So we'll look for the residual function in this form. Our parameters will be lambdas, of course, and the centers and this width W. So numerical solver changes the parameters of the function to match the target values of learning points. So it's easy again, nothing very complicated. These centers C align, our initial dimension D. So there is no dimension switch as we do, for example, several layer network. Simple thing, but efficient. So of course, to address zero asymptotics, we do not let the bells have arbitrary centers. As I said, to guarantee zero asymptotics, we should specify a boundary where we need to restrict them. So first idea, in line with the spirit of data scientists, is that to modify the custom loss function, which penalizes the bells which get closer, which get out of the asymptotic control. So imagine we have a bell out of the asymptotic bounds, and then we don't like this guy, of course, because it will change our asymptotic. So we will penalize the function. However, according to our experiments, much better solution is you mapping function which makes sure that the bell centers and the widths are in the right region. So we restrict the bell centers and their width such that they do not go to the asymptotic area with non-trivial asymptotics. So we make sure that all the bells lie in sort of bulk, such that they go out of it, reaching the asymptotic area will be being zero. And we did experiments with a few hundred of such bells. It's more than enough to have excellent precision for our tests. Right. As numerical experiments, in our paper, you can find the Black-Scholes, of course, Black-Scholes experiments, and more complicated four-dimensional Saber model experiments. So we'll see how it will work in this presentation. An example of this on this Saber model experiment. As far as this science is pretty experimental, we will spend some time describing what we do and what model we use, what kind of hidden parameters we use, and so on. So in our experiments, we will test the normalized Saber model, which is written using this SDE. So we have V sort of approximate the demand volatility. Alpha is a stochastic volatility factor, starts from 1. S is our rate, which also starts from 1. We have the parameter here. We have vol gamma, and we have correlation between these two values. Sorry. So exact option price can be calculated analytically. So we can find actually in this book the available formulas, and so we'll fix the correlation to be 0. Because otherwise, if we go with the simulation for the Saber model for large strikes, for large spots, and so on, it will require enormous number of simulations, such that sometimes we'll never hit the accuracy. So we'll fix the time t equals to one and studied normal implied volatility option of observed option. So we have a function of 4 arguments. Sigma is a normal implied volatility of this process. It has a V as the initial implied ATM vol, beta skew parameter, gamma vol, and psi k. So again, all the experiments can be found in our SSRM paper. So to demonstrate the flexibility of our approach, we control asymptotics in some, but not all the dimensions. And for comparison, we perform 2 experiments. So the first one is we control the asymptotics in the dimensions of the Van roll and the strikes. So only two guys are controlled, volatility and the strike. And we let our neural network extrapolate in beta and gamma directions. So beta and gamma are out of control. Second experiment is we control asymptotics in V and gamma. So we include also vol, while B is out of control. So we do these experiments just to compare how it works for the accuracy. So we do normalization of our parameters. So instead of working with V, K, gamma, and beta, which have different scales, we normalize them such that we call them Z1, Z2, Z3, and Z4. So these guys will span between like -4 and +4. So they will have Gaussian sort of span. And we'll work with these normalized variables. It's often quite useful to take initial variables with different scales, with different signs, and so on, and to map them to something which has sort of Gaussian properties, such that it's situated between -5 or 7 +7. And then it corresponds to Gaussian. So of course they are not distributed, so it's not parameters, it's not distribution. But we just in our numerical experiments we convert them to we normalize them to such a range such that we can simulate them in a Gaussian manner. So the bounds. So since all the parameters are normalized, so our Z are standard Gaussian, well, they have standard Gaussian scale, we will use the same bounds in all the dimensions. So the learning bound will be between -1 and 1, so this LL. So we train our neural network. The asymptotics bound, where we glue the asymptotics, will be from -1.5 up to 1.5. And the measurement bound will be from -2 to 2. So we'll measure errors in the whole region. So again, from -1 to 1 will be learn, then from 1.5 to 1.5 we will impose asymptotics and we'll measure in the larger region of -2 to 2. Of course, the asymptotics bounds are relevant only for the asymptotic control dimensions. If there are no controls, we just ignore these things. In the table below, we show more or less what does it mean for the initial Saber bounds, just to see how far we go. So we learn the parameters, volatility from 3% or 60%, beta from 2% to almost 1, gamma from 30% to 2.4, and the strike from 1/2 to 1.6. Remember the initial value, the spot is 1. Asymptotic bound goes further, so 0.16. You start with 2 times more for volatility. Beta is also quite large. Well, we don't actually impose any parameters for beta. Beta is just it's fixed. Strike goes further up to 3, right, and close again to 0. And we measure all these errors and so on from much larger interval corresponding to volatility from 0.8 basis points, 80 basis points, up to 3 very large values, and the strikes from 0 to like 13. So you see that our measurements go quite far. So how we construct the things? A bit more details. So in the asymptotic control, we use a rather sparse grid of 3 nodes in each direction in our 4 dimensions. So we have -1, 0, and 1 in our normalized values. So we calculate this spline. We attached the asymptotics to that, and we used this spline as a control variable. So as we said, the goal here is to control asymptotic and not necessarily having close fits for this loaning region. So we remove this asymptotic out of the initial function, and we train our layer, which we call as a constraint radial layer, to the residual function. So first we take function, and second we calculate a spline with the same asymptotics. We subtract the initial function from the spline, so we have a residual function with 0 asymptotics in certain dimensions, and then we approximate, we train our constraint radial layer with the Gaussian belts, you remember, to this residual function. So it's 4-dimensional function again. So it consists of 10,000 Gaussian samples. Then we convert them, of course, to the initial parameters of the saber. Of course, we ensure that all these 10,000 points lie inside this appropriate region, which we have defined above. We reject the points which can be outside. Then this constraint radial layer is used to fit these asymptotized values. It has 300 nodes, 300 Gaussian channels, which we move in different directions, and about 2,700 parameters to train. For control dimensions, the center and widths are within the right bound, so we control them. We control force the Gaussian belts to be inside, just parameterizing the widths and the sensor to be in the right bounds. For uncontrolled dimensions, there are no bounds such that the Gaussian kernels can go outside in these dimensions. So we compare our results with the standard neural network. You know, it's building 3 layers, 3 activation layers with sigmoid activation functions, and with certain number of nodes, that the number of parameters is 2,700, so very close to this neural network. So when the approximation to the same volatility is learned, we generate a validation sample which covers the larger measurement region, so the whole measurement region from -3 to 3 in terms of the normalized parameters. So and we see what goes there, which we'd like to see where the main errors and so on. So first testing is about the errors, of course. Without doubt, our test showed that controlling asymptotics significantly improved the neural network fit to saber implied volatility. So the output here is mean squared errors. So we check the neural network against the exact results. We work with the normal volatilities and the average values in the bulk, which we have calculated is quite high. So it's not just normal volatility of 1% we get used to, but as far as we go outside in different directions, we can have it much bigger. So this is in the learning set. However, it can be much bigger at the edges if we go really far. So learning error is a mean squared error over all the learning points, right? Then we concentrate on validation error of another simulation set. And inside this validation error, we will distinguish the learning, asymptotics, and measurement regions errors, such that we pick up the points, for example, of this validation set line in the learning frames, calculated error, then we do it for the asymptotics and measurement and the whole. So we'll see that everything is more or less consistent with our theoretical constructions. So who is who now? So model 1 is our Gaussian Bell network, where we control the volatility, the strike, and the volleyball. So it's the best guy. Model 2 is Gaussian bells, where we control the volatility and the strike. Model 3 is our baseline neural network with 2 layers and the sigmoid as the activation function. So deep and endless 2 layers. So this is a table with main table with errors. So we have matched all these 3 models to have the same learning errors. So learning error here was 2 basis points, so very nice, for all the 3 models. So there is of course a little difference, but it's due to Monte Carlo noise. At 2,000 points, it's more than reasonable fit. Now we have for our simulated validation points, we say that the overall error in the whole validation region will be very, very different. So for the first model, it will be 70 basis points. For most precise model. For the second one, 2 times more. And for the model 3, where we don't control anything, it can be very, very big, 15%. Now let's see what happened in this validation point. So the validation points which fall into the learning error has more or less the same error. So we have 9 basis points, 8 and 7. Again, there is a noise between them, so we consider them as to be very close. Due to certain interpolation errors, it is larger than the initial ones for the learning error by like 4 times larger, or 4, 3, or 2, or things like this. So we do interpolation, of course, makes the initial fit less good, but still quite nice. So 9 or 8 or whatever basis points. Now in the asymptotics region, so in the region between where we start asymptotic start, they have different scale. They can have 49 basis points, 1.3%, and 2.6. And the whole region, we can, measurement region outside, we can have very, very big numbers. Yeah. So this one is still very moderate, 1.2, and the other 2, this is also, but if there is no control, we just get out. We get out completely of the thing. So this is more or less what I have expected. So let us check it. Let us check on our graphs. So all 3 models fit the input equally well. So for the learning point, of course, so actually we have tried to, this one was one of criteria of our experiment. So all the models should do the same learning error, but we would like to see what happens outside of it. So over validation points, also the errors were more or less the same due to little interpolation tricks. So model 1 and 2 outperform model 3 significantly outside the learning region, of course, and model 1 outperforms model 2 because we control more asymptotics, more dimensions. So again, we will visualize the graphs here. We will fix 2 parameters, and we will make graphs of the 2 graphs. So more plots can be found in our paper, but here just I put several things, several plots to these slides. So let us fix beta and gamma and plot errors as a function of the ATA vol and strike. Again, in the normalized value, so from -4 to 4. So we see here on this graph that the errors in the learning area from -1 to 1, very nice. This guy is what happens between the learning area and the asymptotic. So asymptotic starts here at 3, so at 2, sorry, and so this spike is what happens to this function because, well, it's of course there is no control here, so that is why we can expect more errors here rather than elsewhere. So here the asymptotic is 0, so by construction here the error is very small due to the learning feed, but here outside we can have some imperfection. However, if you take a look at the scale here, it's pretty small, 0.003, like 20 basis points here, which is pretty nice. If you take a look at the neural network without any control, we'll have a completely different scale, goes to -4. So of course everything is good in this learning area corresponding to -1 to 1, so d square. But what happens outside is completely out of control. Now, to show the effect of controller asymptotics, we'd like to visualize our models 1 and 2, and to see what happens if we do not control one of the dimensions. So here we have gamma, normalized gamma vol, and here we have a strike. So in one of experiments, we do not control gamma. So this means that the errors outside of the learning region here are out of control. So there will be some values here. So of course everything is okay here. All is good in the direction of the strike where we control the asymptotics. However, outside of gamma for large gammas, for large, small, and large gammas, right? We'll have these years, well, whatever it means, but we see that the errors coming up if there is no control. If we do control it, as we have seen, we will see the errors in this no man's land. So here all is great in the middle, in the learning area. But outside, between the learning area and between the area where we control the asymptotics, we have these little spikes here and there. Again, if you check the scale here, it's some basis points, really small, with respect to 5% here and there. So this is an effect of control, where we actually put the whole error in the no man's land and start controlling asymptotics. Right. So as a conclusion to this presentation, I would like to repeat a little bit certain statements of. So while deep neural networks are good in fitting interpolation, well, not always interpolation, as we know, sometimes it can be, we have some big spikes and big holes. But anyway, they are not good in extrapolation. That's for sure, that absolutely nothing prevents them to go out of the function with absolutely uncontrolled rate. So this has consequences for their usefulness in mathematical finance. So performance in regimes which not seen before, it happens all the time, especially with stress in COVID times. Stress testing also can be corrupted and explainability and so on. So if we don't see that we can control asymptotics, then we can say that something goes wrong. So we propose a way to incorporate actual knowledge of the asymptotics into this neural network. So a special spline which removes the asymptotics, then a special layer of Gaussian kernel functions, like Gaussian bells, with restriction to the centers to approximate the remainder function with the zero asymptotics. So our results confirm the threshold conclusions. And actually, you're welcome to ask questions. Thank you very much. How can I see?
Okay, so we've got one question from Benny here that's saying, would you kindly share any supporting research papers and/or white papers on the subject?
Of course, they all at SSRN. Again, yeah, you can download it. You can download it easy. Yeah, no problems. Another thing, which maybe I didn't mention, is that we wanted to understand if there's mathematical result. If Kolmogorov-Arnault theorem can give us some information about the asymptotics when we apply arguments of Kolmogorov-Arnault, then we know the function, and of course this function bears some asymptotics. So if inside this theorem, the question was if inside this theorem we can detect some traces of asymptotics, and actually the answer was no, it is impossible. And so you can check it also at our SSRN paper about this thing. So that is why we wanted to one of the motivation of this function was to see maybe in the Kolmogorov-Arnault we can see some possibility to do the asymptotic control, to choose the basis function, to choose the activation functions, to at least to try to do something. But actually we didn't manage to do that. So that is why we have constructed this this specially designed neural network for zero asymptotics. Another thing which I would like to also to answer is that how can I say, is that the Gaussian networks, the Gaussian Bell network which I have presented, in fact uses centers and widths which have a spatial sense. So in our dimensional ball, we have different nodes which correspond to different Gaussian bell. So they do have a clear spatial sense. So this is space, right? So this is d-dimensional space. However, if we go with some deep neural network, this spatial sense is lost, because we always in all these layers we convert it from the initial dimension to something different. So that is why also we wanted to keep this Gaussian canals neural network in order to get attached to the initial space, to the initial dimension of the problem. Well, anyway, just some speculation. Okay, what is the zero? This is this error which we measure is absolute error, such that, for example, here we have one basic point of difference. And as I told you, the average normal implied volatility for our bout was 20%. So this is to get the absolute relative value, we should just divide it by 20%, 0.2. So again, this 2% of 2 basis points of this error with respect to 20% is very decent. It's very decent in error. Also, 9 basis points with respect to 20% of the average error. That's also quite decent. This is becoming, becoming the magnitude, especially this one of the value of the mean.
Okay, we have a question here from Sam saying, thank you for the presentation. And is the code available in a GitHub repository somewhere?
Actually, no. Wow, but it's not a big deal actually. We have in the presentation we have in the SSRN paper we have quite detailed explanation of this thing. And so I don't know, one can easily implement it using the Keras, things like this. So there are two. So there's a question from Jose. Could it be elaborated more on how the residual is approximated using the Gaussian bells and the neural network? Would you clarify the relation of the Gaussian bell and the neural network? Actually, it's a good question. Let me come back to these Gaussian bells. We have written this the so-called bespoke Keras layer in the following way. So this is one bespoke layer written in Keras, such as derived class, as the parameters as centers and the weights, and it takes the initial x, then we multiply it by these guys. We can do it using this TensorFlow or whatever thing inside it, and then this layer actually stops. So it takes x, and the output is g's, functions of g's for each I, for each Gaussian bell. And the second layer is simply a linear one without bias. We just sum them up. So this kind of bespoke layer, again, take axis. It has about 300 nodes, such that for each node we pick up C of I, and on the weights we construct the output using this formula, and this we are assigning to the node, such that again the last layer, linear layer, just sums them up with some weights, and we get the function. So this lambda is also trainable parameters, of course, of the second linear layer. So yeah, so this is sort of neural network layer manually constructed. Saber, what is the principal decision making? If I know the parameters of Saber model, what is the principal decision making in option market? I didn't quite understand this question. Maybe you can explain a little bit what did you mean? Making an option market. At least, as far as I understand, maybe you meant that why do you would like to use this neural network approximation rather than calculating the model itself? It's the question. Then it was just to show that in multidimensional scheme this will work, and also that for the Saber model we know the asymptotics. Also, so we know that the model is heavy, but we know the asymptotics. So that is why it was a good toy object to work with. So I wouldn't put it, directly the Saber model to the production. I would better use the analytical functions. But for us, it was just exercise, the multidimensional option. Some participation cases feeding out of the money balls were challenging at best as compared to the money. We don't have opinion on that. Wow, this I don't really. Of course, as if I understand, this doesn't have any relation with the neural networks, right? So just the question is why the fitting. Maybe because when we approximate the option price, not the option volatility, it is for the out of money balls, it is more sensible with respect to the prices. So maybe because of that, so it's less flexible from this side. But otherwise, the Saber feet, again, the Saber model can have actual degree of freedom. You know, we can add here and there, such that we can control both links. But concerning the Saber model itself, it's hard to say that. I don't know. There's maybe some asymmetry. In this case, one is more flexible than the other. Could you elaborate how this technique can be used in model calibration? Yeah, in model calibration, I can also refer you to a paper of Blanka Horvat in a recent paper in Risk magazine, where actually she with her colleagues they worked out how can we, what is better to do directly model calibration using the neural network, meaning that the model calibration is the output is whatever function on where the function is the volatility for whatever strike, and the inputs are the positions of this smile. So one of the conclusions, again, for some models, was that it is better to approximate the price itself, or and then use a solver to invert it to the calibration rather than to calibrate it directly. Again, this I don't really know. I didn't touch it numerically. But it can be important to distinguish between the final result of calibration, as I said, as an interpolation for some smile given the points on the strike, and or as alternative to calculate to approximate using neural network the option price given the parameters, and use a solver which will match these parameters to the given values, and then interpolate it using these fixed parameters in the neural network. So somehow the second way was better, but again, maybe something went wrong, and this I cannot say to 100%, but I can refer to Blanka Horvat paper. Yeah, about the negative interest rates, you can use the Saber can go to interest rate. To negative interest rates, for example, let me come back to the initial formula for this one. So this Saber which we have used was a Saber with an absorbing boundary. So it goes to 0 and then it stops its life. So S cannot be less than 0. So there are ways to extend it to negative rates. For example, we can just remove completely this term. So if we remove this S of beta, we will have sort of Saber generalization of a normal process. Imagine alpha equals to 1, just without gamma equals to 0. We'll have normal guy, right? Then we add this. When we add this alpha, we'll have something around a normal model. So I tried to calibrate this normal Saber model to the current market, and it fitted quite well, in spite of the fact that we have fixed this beta, we didn't calibrate it at all. So you can read about this normal Saber model without any boundary in our in this book actually, or underlying papers. Its solution is very simple, just one-dimensional integral. You don't need to do whatever with the edges and so on. This formula works very fine for whatever maturities. It's very fast. So I would recommend using this normal Saber model with beta equals to 0, such that it can cross the boundary here and there without any problems. But it will have this stochastic volatility here. So very simple model. It has simple closed form, and it can also you can fill the parameters with what do they mean. Any other questions? Cool. Thank you very much for your attention. And yeah, talk to you next time. And thank you to WBS for organizing this event. Thank you. See you.
Thank you, Sasha. And yes, this recording will be going up probably tomorrow on the Quant Hub YouTube channel for everybody that wants to see it again, along with the presentation itself.
Thank you. Thank you.
Thank you.
Okay. Have a nice evening.
You too.